This is the last section before our test, okay? We've spent a good amount of time now in chapter 19 talking about the idea of electric charge and electric forces, those two things. Now, because you guys already started the lab, the electric field hockey maze lab, you kind of have an idea already of what you're going to see in this lesson, to give you a little preview, okay, of electric fields. It's an idea of what you're going to be working with. So the ideas that we're covering today are going to be an extension, as always, of the other stuff that we've learned. So we're going to first talk about field strength, and then we're going to talk about how to draw field lines. It's not a very difficult lesson, and the math is rather simple. I'm going to show a little derivation of the formula, okay, right here in the first slide. So let's take a look at this first note slide, really. So in this example, we want to look at the idea of electric fields. And if you recall from the lab you started, when you put a positive electric field down, or electric source, or a negative electric source, you saw arrows that would come either out, or arrows that would point in toward the source. And depending on how far you got through the lab and how much you did, you saw more or less of this. But the idea is the following. Here's the idea. The way we draw field lines from a source is to consider that that source is in the proximity of a proton. Now, I know it doesn't make sense because usually electrons are the things that move, but the traditional way that physicists started to do this, like hundreds of years ago, were that we look at a positive, what's called test charge. Okay, you see that phrase test charge in the definition. So here's what I'm saying. Let's say we've got an orb, okay, like, what is it called? Ever heard of a Van de Graaff generator? Have you ever seen this thing before where somebody touches and it causes their hair to stand up on the ends? It's called a Van de Graaff generator, and it's physically a sphere, usually metal or like plastic of sorts, actually sometimes, the newer ones, that if you touch it, you can sometimes see what looks like little lightning bolts coming towards your hand, especially the ones that are clear or transparent. But other ones that are made out of metal, you can actually transfer that charge into your body. So this is like the Van de Graaff generator right here. It's a fixed thing in space that is not going to move, that is generating some sort of a charge. Now, if I were to take a proton and bring the proton near a positive source, two positives are going to repel, so the proton would be pushed to the right. So that's what you're physically seeing right here with this arrow. Now, if I take the other scenario, the flip side, and I look at a negative source, Maria, focus please. I take a negative source, and I bring a proton near it, the proton is going to be pulled toward the negative source, which is why this arrow here is drawn to the left. So the arrow in these field lines, which we're going to see in a minute, just indicates the direction that a proton would move. The direction that a proton would move, okay, in the proximity of this source, whatever the source happens to be, positive or negative. Okay, positive or negative. Clement's question, or you're just fixing your arm? You had a hand up though. Was that a hand or? Okay. So to really take a look at today's lesson, we need a couple formulas. And this is the newest formula we're going to write down. And this is the one that's on your formula sheet. Okay, there are two new formulas from this section that are going to be on your formula sheet. The first one I just circled, and then the last one all the way at the very end that I'm circling as well. Now, in between that, I did a little bit of algebra. That's all that happened here. And let's take a quick look at what I'm referring to. So let's say I solve this equation here, solve this for E. To solve this for E, I would divide by Q0, right? Divide by Q0 to get E by itself, and that's what this equation is. So I solve for E, it's FE over Q0. Now, what I recognize over here, though, is that FE has its own formula. FE is KC, Q1, Q2 over R squared. Why am I not using Q1 and Q2? Because in this problem, well, this is really Q1, and this is really the second object, or this is really Q1, and this is really Q2, right? That's where they're referring to in these particles here that are shown. So because I called this Q in the diagram, I'm just going to use the letter Q for now. Because I call this Q0, the phrase with a zero means like an initial usually, initial charge, but it just means some charge of arbitrary nature. I'm going to call this Q and call this Q0. And instead of calling it Q1 and Q2, they appear right here. Right? But this is really Q1 and Q2, just like we did in 19.2, 19.3. But the reason I do this is because now this Q0 cancels with this Q0. Those two things drop off. If I cross them off, I'm going to use yellow to show this. If I cross off Q0 here and here, what I'm left with is KCQ over R squared, which is exactly this here. But it's important to note, write a little note for yourself, that this is called the source. Whereas this in this formula is called the test charge. So they're two different things. The lowercase q is called the source, just by itself. It's whatever is giving off an electric field. Just like the Earth is the source of a gravitational field around us. Just like your body is the source of another gravitational field. Just like this calculator, because it has mass, is a source of a gravitational field. Anything with a charge to it is a source of an electric field. The thing that has more of a source has more charge. So the test charge that's brought nearby is like 1 proton, whereas this is like the value of, say, like 50 protons. So it's like, why don't I really pull on the Earth? Remember that same question? Because my gravity is insignificant compared to the Earth's. Just like these little protons are not going to move the source. So if this proton is brought near the source, it's going to get launched back. If this proton is brought near the source, it's going to get pulled toward it. But the sources are fixed. They're not going to move. They're fixed in space.
They don't move at all?
No, the idea is that it's literally an object that is stationary because it's maybe drilled into the ground or its post is drilled in. So these are stationary things where the other object is brought in the proximity of it. And our goal in this lesson is to figure out, well, how intense, what is the intensity? How intense is this electric field? And it was actually one of the answers in Jeopardy. Remember, so you guys didn't do this lesson yet, so one of those Jeopardy questions I sent you in the video was newtons per coulomb, and the capital C stood for coulomb, and that comes from these units we're going to see right here. Newtons per coulomb. Okay, this is an electric field intensity. That was the question that they were asking about there. And the units make sense also, right? The units make sense. The units of this numerator here is newtons. The units of this are coulombs. So this whole thing is newtons over coulombs, newtons per coulomb. I could also see that right here. Force is measured in newtons, charge is measured in coulombs. Newtons per coulomb is electric field units. So these are going to be our units on the far right. So what we're trying to look at here is how strong is the electric field? That's what we're going to be figuring out. What does R stand for again? These problems, what does R stand for? It's not radius, right? It's not radius. Yeah, it's the distance. So in this case, it's going to be the distance from the source. The distance from the source. Okay? Which is the same thing as the distance between these two particles. Right? The distance from the source is how far the particles are apart. The distance from the actual source. And by the way, in case you're wondering, this is analogous to the following. Just like we showed analogous nature in the last section, this is analogous to writing this. Right? Is it weight equal to mass times gravity? I wrote it backwards for a reason. Little g was the gravitational field. Capital E is the electric field. Little m is the mass. Q0 is the charge. So these are properties of the object, and then the E and the G are field properties. So again, these equations are very similar to what we studied with gravity because of the correlation between gravity and the electric field itself. Okay, because of that correlation that exists. Let's take a look at some examples of some stuff we're going to look at for field lines now. Okay, for field lines. I cross off, oops, go back, sorry. So this is the next slide here we want to take a look at. And if we think about this, all we're going to do is draw the direction of the arrows, that a positive test source would go in. So if I bring a proton near a positive source, the proton is going to get pushed away from the source. So all the arrows are drawn away from the source. If I bring a proton near a negative source, the proton is going to be pulled toward that source. So all the arrows are drawn inward or toward the source itself. So a negative and positive test charge yield different field lines coming from them. Okay, yield different field lines. You could use the phrase, if you want, that these lines are drawn radially outward, and these lines are drawn radially inward. Okay, that's a phrase that you might use. If you study a little bit more physics, or even next year in AP Physics, you'll definitely hear that phrase. This is radially outward. These are radially inward. Radially means in the direction of a radius, if it were a circle. So think of this as a circle where all of these arrows are like little radii. That's why it's radially inward or radially outward. Each arrow is like a radius. And that's where that phrase comes from. So there are some rules that we want to look at for field lines. Okay, there are some general rules, so let's take a look at them. The first general rule is this. Field lines can begin on positive charges, like we saw when we draw them outward, or they can begin at infinity, and we'll talk about that in a second. But they must end at negative charges, meaning they converge on the negative source, which we saw in the last slide. All the arrows ended at the negative charge, or they can end at infinity. So the first one we'll take a look at a diagram in a minute to help us with. The second law says that we are going to look at the number of field lines and how it's proportional to the actual value. So although this is not mathematically exact, if I'm drawing a diagram and I draw one diagram, right, one diagram with 8 field lines coming out, and the other diagram with 24 field lines coming out, I can make the conclusion that one of the sources is triple in magnitude or strength. So physically, the number of lines. So if I have a lot of lines coming outward, it means it's a very strong field compared to the other one. But that's a relative statement, relative. So I need to be comparing it to something else for that to make sense. And then the final one is that field lines can't be crossed. Field lines can't be crossed. Okay, so let's take a look at some examples that can show these 3 rules, and we can see them a little bit more clearly. So looking at these 3 examples here, the first one, I'll start with them one at a time. We'll kind of zoom in and zoom out a little bit. The first one is probably the easiest because we have a positive and a negative charge. So if I'm a proton, I'm going to want to move toward negative charges because I'm a proton and I'm a positive charge. So I'm going to get pulled physically toward this blue charge. And look at all of your arrows. Where are they all pointing? Toward the blue charge. Now, on the other side with the positive, what we'll notice here is that some of these arrows don't loop around. Like this one loops around, right? It comes toward the negative charge. It starts moving away from positive toward negative, away from positive toward negative, from infinity toward negative. But sometimes some of the field lines are going to be drawn leaving the positive source and going outward. And this is what I mean toward infinity. So field lines have to start on the positive source, or they start out here at infinity somewhere. They have to end on the negative source, which is why all these arrows are drawn toward the negative source, or they can end somewhere out here at infinity. But the idea is that it's always going to start on a positive, end on a negative. The infinities are the pieces that we don't know about. Again, just a sketch. You don't have to be able to, perfectly create this, but you need to be able to get an idea of what this looks like. If you're given a problem and ask you to match it up or draw a diagram of this, you should be able to start by drawing all your arrows away from positive, all your arrows towards negative, and some of them that come away from positive end up curving and going back toward the negative. Some of them just come toward the negative from infinity out here. Some of them leave the positive and go toward infinity over here. But the idea here is how the field is distorted around the source. Now, if you want to see a little better example of this, use that simulation. Use the electric field hockey simulation and go ahead and put a positive and negative source next to each other, and this is what you'll physically see. If you want to investigate maybe 3 different sources, then what would happen? Take a look at how the field lines are distorted. Okay, but for now, the theory is what you're going to need to know for field lines. I'll get into the math part in a minute, where you're going to calculate the strength of the field, but as far as field lines are drawn, you really need to know the theory, the conceptual stuff for these field lines. The second example is when we have 2 of the same sign. So these could be positive, positive, or negative, negative. And what we know is that 2 positive signs, what do they do to each other? 2 positive electric charges They repel. And physically, if you were thinking back to your childhood days where you played with magnets, when you took a North Pole and a North Pole, they repel. Same thing as a positive and a positive, theoretically. And what was the feeling you had? Didn't you feel like they were literally being like pushed apart? You physically can't get them together. Every time you got the magnets closer, the repulsive force got stronger because it's over r squared also, by the way. So as you get closer, the magnetic force gets stronger and it pushes more away. That's what you should be visualizing in your mind. There's like a barrier between these that is preventing them from getting any closer. And that's the field lines that you're physically seeing. With a magnet, the field lines are the same, actually. Field lines from North Poles exit the North Pole and come back around to the South Pole. So field lines on North to North Poles like this will show the exact same diagram. So what you're seeing here is if I were a proton and I were placed over here, I would move in this direction. If I were a proton placed over here, I would move in this direction. But if I was a proton placed in the middle, smack in the middle, like literally just in the middle, what would happen? Right? Why not, Graham? All right, you're halfway there, Maria. You're halfway there. Somebody help her out. Maybe be a little more specific about the statement. Here?
Is that correct?
Say it?
Is that correct?
I'm not telling you that's correct. I want to hear more feedback. What do you think?
I think it would stay in the middle.
You would stay in the middle. Okay. Chris? You would say it stays in the middle also? So Maria, your answer could be right if you made one more clarifying stipulation at the end. For now, though, if it's smack in the middle, that's why I made this point to say that, it's perfectly in the middle, it won't actually move. Because both of these sources are going to push it away, and it'll be a state of equilibrium. But this is an unstable position. It's a very unstable position, because what happens if I move it just for an instant up? What's it going to do? It's going to move up. Yeah, it's going to continue upward. If you just give it a little what's called perturbation. Perturbation is a little push. Give it a little perturbation down. It's going to move down. This is called an unstable system, just like what's called, or just like an inverted pendulum. We haven't studied this yet, but in engineering it's a big topic. So we've studied the pendulum, right? Here's the pendulum. Right? And it's very stable. But what happens if I take a pendulum, ready? And do this. Imagine there's a rod connected to a mass at the top, and it's perfectly straight. It's going to sit still, right? But what happens if I just push it to the right an instant? What's it going to do? Just a little push. Yeah, it does that and falls to the bottom. What if I push it this way a little bit? It does this and falls to the bottom. So this is an unstable system. It's like a ball at the top of a hill. Imagine a soccer ball at the very top of a mountain. And you push it a little bit, imagine the mountain comes to a perfect peak. I know it doesn't, but imagine it does. If you push it just to the left, what's the soccer ball going to do? It's going to fall to the left. Push it just to the right, it falls to the right. It's an unstable system. That's another example of an unstable system. The inverted pendulum, a ball at the top of a hill. The opposite of the ball at the top of the hill is a ball at the bottom of a valley. And that's the same thing as a pendulum on the bottom. Think about it. The ball at the bottom of a valley does this and eventually stops. It's stable. It goes to a stable point. At the top of a hill, though, it would fall off and never come back to that spot, right? That's unstable. Just like here. If I give this a little nudge upward, it'll get launched up and it's never going to come back to there. It's unstable. It's unstable. Okay, these are just phrases I'm using. I'm not going to ask you about unstable and stable on the test, but it's just some background knowledge for some more advanced physics and engineering.
Also, what would be the opposite to make it completely stable?
For something like this, you'd have to have a system of sources for sure. You'd have to have a system. A system of sources, or honestly, just a negative source somewhere. Imagine if I had this, Steve. A negative source, okay? And I bring a proton near it, right here. It's going to do this. This is a stable system, actually, because what it'll do is this. It'll get pulled toward this. It'll go past because it has inertia. It'll get pulled back. It'll go past because of its inertia. Pulled back, pulled back, pulled back, pulled back, until it eventually stops, right? So it'll be like this. It'll eventually stop. Like a fin or like a diving board. A diving board would be a stable system. It starts here, you bend it, you perturb it. What does it do? It goes, it stops, right? It's a stable system. It's coming back to its equilibrium position. Same thing as this, whereas this would not be stable. It's not going to come back there. Okay, but again, you won't be tested on those terms of stable and unstable systems. I just want to give you guys ideas. Last but not least, let's look at an example of a positive and negative, though, with different charges. In the first example, we had a positive source and a negative source of equal magnitude. And we saw the field lines were pretty much the same. But now, we have a positive source with a lot more intensity. We've doubled the strength of the negative source. That's why there's a 2 there. So as a result, if I look at this carefully, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 field lines coming out of there. And going into the negative one, 1, 2, 3, 4, 5, 6, 7, 8. 8 and 16 have a ratio of 2. Look at the magnitude of charges. This is double this one. And because it's double the field strength, physically what we're seeing is that the field lines from the positive source continue outward further. They continue outward because they're the overarching or stronger of the two fields. The stronger of the two fields. Okay, with that said, I want to get into some math. We got 2 problems to do. Let's jump into it. So a charge of 10 microcoulombs produces an electric field. I use the word produce, so what is that? Is that the test charge or the source? Is that the test charge or is that the source? It produces it. The source. Think about production. If you want to produce energy, you need a source of energy. The source is what produces the electric field. So Q of 10 microcoulombs is indeed the source. Determine the electric field at a point 10 centimeters from the charge. So that's our R value. Then determine the electric force felt by an electron at that distance, and will this force be attractive or repulsive? So let's take this one step at a time. Here's Q. Okay, if we didn't know that, we have to recognize that micro means 10 to the negative 6. So I replace that. The distance from the source is 10 centimeters, which is 0.1 meters. Pretty much it. Don't need anything else to find the electric field. The electric field formula is pretty simple. Okay, we have one of 2 options. We can use this formula, or we can use this formula. Either of those 2. We are trying to find the electric field. That's capital E. It's in both equations. Which equation am I going to use, though? 2 givens, make sense of it. It's pretty logical. It's quite straightforward. If I just use my givens alone, which formula contains my givens?
E equals KCQ.
Yeah, right here. Okay, we'll ignore the first one for now. So it just makes sense to use the second formula. Kc is a constant, Q is the source charge when we're given the source charge, R is the distance from the source charge, and we're putting that in the formula. So let's go ahead and plug and chug. We've got E equals 9 times 10 to the 9, and that's, let me show the units just for the sake of one of the examples first. My units are, for N, if you remember, for K are Newton meters squared per Coulomb squared. You don't have to memorize that. Again, it's on your formula sheet. Times the charge all over the distance squared. Makes sense of the answer. Meter squared cancels with meter squared. Coulomb cancels with one of these coulombs, leaving newtons per coulomb. And newtons per coulomb is the unit I want for electric field strength. Okay, units of newtons per coulomb. Peter, what's up?
Why do you convert R to meters?
Because what's my base unit in length? Yeah? It's given in centimeters. Be careful, right? If it's given in millimeters, micrometers, kilometers, anything, you always go back to meters. Remember, you always go back to the base unit except for kilogram. Kilogram is the only one that's not used without a prefix. The base unit of mass is kilogram, which has a prefix, which is very annoying, but there is rationale to that, which we kind of went over already. So the answer becomes 9 times 10 to the 6th newtons per coulomb. I'm not going to spend time checking your work today. So you need to practice this yourself. If you're not getting this answer, and you've typed this in, or at least you think you've typed this in properly, and you're not getting the answer, you're clearly making a mistake somewhere. I'm not going to stop today to go over that, but that means that you need to write yourself a note that says, hey, stop by and see Mr. Howell someday about scientific notation and these formulas. Okay? Because if you're not getting that answer, you're making a mistake with your calculator. Now, with that said, let's move on to the second part of this problem. The problem doesn't just ask us about the electric field. It then says, determine the electric force felt by an electron at this distance. Electric force. I've got two equations for that. I can go to this one from last section, or I can go to this one from this section. Now, I'll tell you right now, both will work. Both will work if I try and both. You don't get the same answer for both, so it's fine. But one is more optimal route than the other. Right? When I want to go from A to B, I go in a straight line. Or a long line of some sort. But I go in the fastest route possible, right? I go in the fastest route possible. Which of these equations takes the faster route?
The second one.
Yeah, how come?
Since it's given. We found E and then she was given.
Yeah, again, and be careful, it's not the one up there, but it is given. We'll talk about that. We already found E. Isabella picked up on, we have E, so why go about doing this all again, right? It's not worth it. But what's Q0? It's not the same as that Q. It's not the same as that Q. Remember, Q0 is the test charge. It's the object that's brought near the source. What object is brought near the source in this problem? What object is brought near the source? An electron. So what's the charge on an electron? Remember, the electron is brought near the proximity of the source. And the question becomes, well, you need to write down what Q0 is. What's the charge on an electron? What's the charge on an electron? It's on your formula sheet if you don't memorize it. You don't have to memorize it. It's on there. But what do we have? Do you remember it? Negative.
1.6 times 10 to the negative 19.
Very good. Negative 1.6 times 10 to the negative 19. So again, this was the given in this problem to start for the electric field, but the test charge that's brought nearby is really just an electron, which is really negative 1.6 times 10 to the negative 19 coulombs. So this is the charge I'm going to use for Q0 right here. And I've got the capital E value right here. I can multiply those two numbers to figure out the force felt by the electron. So I've got my answer for 9 times 10 to the 6, and that's newtons per coulomb, times the charge on an electron, which is in coulombs. Coulombs cancel, leaving me behind with newtons, which is what I want. Right? Coulomb cancels with coulomb. It leaves me with a very, very, very small force, but this is actually a really large force for an electron. Right? Everything's relative. Everything's relative. So this force that we get at the bottom, this one's really small, right? 0.0144. 11 zeros and then 144. It's a really small amount of force. But if I'm an electron has almost no mass. So even the smallest amount of force for an electron, that thing is going to shoot off at a ridiculous speed. At a very, 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 very high speed. Okay? So if we want to think about those of you that are considering AP Physics next year, you might want to consider the fact that you might have to take a problem like this, where you find the overall force, and then you have the mass of an electron, and from that you can find the acceleration, because F equals ma. And if you have the acceleration of the electron, after a certain amount of time you can find the velocity, right? Because F equals Vf plus at. And then with that velocity, maybe it collides with a proton, and you could use inelastic collisions to calculate the energy loss between that collision. And you could also find the impulse. There's so much you can do to connect all of the lessons we've done. And I want to give you an idea how force is still related to the beginning of the year. Okay, it's always related back to the beginning when we're learning about forces. Now, I didn't put negative here. I didn't put negative. But clearly, isn't there a negative number here at the bottom? Why did I drop it? What's going on here? Why do I not care about the negative? What does the last part of the question ask us? What does the last part of this question ask us about?
be attractive or repulsive.
Yeah, attractive or repulsive. And if you recall, the negative sign indicated something. When we had a two-particle system, which is what this is, a source and a test charge, two particles, when we got the negative sign as an answer, it meant attractive. A positive sign meant repulsive. So I can carry the negative sign over and just remember my rules. That when I get a negative answer like that, it means that it's an attractive force. Okay, or I can just physically look at the example. Positive source, a negative test charge, opposites, what do? Opposites attract. The answer's got to be attractive. So whether or not you put the negative here is not actually as important. And I told you about that on your test also. Okay, so for your test when it comes to next week, if you don't make the charges negative and you make an overall positive answer, it's not the end of the world. Okay, we just consider the fact that it's a positive or negative, indicating that it's attractive or repulsive. Okay? The example for today has to do with two sources separated from each other. So let's put two sources with a distance between them. They're separated by 40 centimeters. Here's my sources. Q1 is 3 times 10 to the negative 8 coulombs. Q2 is negative 2 times 10 to the negative 8 coulombs. I want to know what's the electric field at that location X, the halfway point. Since they're separated by 40 centimeters, I know that this is 20 centimeters, and I know that this is 20 centimeters. I also know that I'm having a positive and a negative source. So if I'm a proton, right, what I care about is being a proton. If I'm a proton, which way am I going to be pulled? If I'm a proton, which way am I going to be pulled? If I'm in the middle, I'm right here, and right here. I've got a positive source here, I'm positive. I've got a negative source there, I'm still positive. Am I going to be pulled toward the negative or pulled toward the positive? Yeah, the positive pushes me away as it is, doesn't it? And the negative pulls me. So I'm getting pulled this way from both fields. From both fields. So at that center point, both fields are pushing me left. Right? My field lines are always drawn, okay, in that direction. To the right, not left. I'm doing it reverse now from my direction from you guys. Both field lines are pushing me to the right in this direction. And that's how I draw my field lines away from positive and negative sources. So what I have in the middle, believe it or not, is I have a pull from the negative source. I have a push away from the positive source, which are both really pushing me or pulling me to the right. So I can find the electric field from one of them, the electric field from the other one, and then if I want to figure out the overall electric field felt, what should I do with those two values? Yeah, sum them together, because they're both causing me to move to the right. Okay, that's the process I'm going to undergo. I think we're going to run out of time in a minute, so I wanted to make sure to get that written down. So if I want to write this, though, to see it, I've got KCQ1 over R1 squared, KCQ2 over R2 squared. I'm calling them Q1 and Q2 as sources now. It's the same thing as calling these Q. I'm just giving them subscripts because I have two different sources. Don't let this confuse you with section 19.2, 19.3, where we found a force. And we did KCQ1 times Q2. This is still the electric field formula from this section, where this was just Q a minute ago. But because I have two different sources, I have to give them subscripts. I can't not. Okay, so the first one becomes 9 times 10 to the 9 times 3 times 10 to the negative 8 all over 20 centimeters, which is 0.2 meters, squared. That's the first electric field. Now, again, I'm not caring about the negative signs in these sections. I'm not caring about them. So for the second one, I'm going to have pretty much the same formula, except this is going to be a 2 times 10 to the negative 8. But again, over 0.2 squared, because the distance is still 20 centimeters from each source. Again, I know that this is really negative, right? It's negative 2 times 10 to the negative 8. But I'm not caring about that because I already took into account the direction that the proton would move. So if you want to be safe, some of you have been doing this is fine, right? Put your absolute value lines around everything. The first electric field is 6750, and that's newtons per coulomb. The second electric field is 4500 newtons per coulomb. But both of these sources are causing the proton to move to the right. So I'm going to add those two numbers together to give me an overall electric field of 11,250 newtons per coulomb. Okay, 11,250 newtons per coulomb. So again, very similar to 19.2, 19.3, but we're looking at a source that provides a pull in one direction or a push in the other. Again, this homework is not due tomorrow. Tomorrow, what is due is your problem set. You should have only this section left. Everything else should be done at this point for your problem set. So finish up the problem set for 20-1 tonight. You have a lab that's due next week, and you have this homework that's due next week. Please see Google for those deadlines. Okay? Have a good day, guys. We review tomorrow. We review tomorrow in this class for next Wednesday's test. Unfortunately.